Now, in order to ensure the correctness of your sequential circuit, so after you have implemented your sequential circuit and you have the circuit diagram, you need to verify, okay, the correctness of your sequential circuit. And the way to verify this is that you need to ensure that it produces the original state diagram. You can verify this manually by hand, or you can use, let us say, the help of a simulator. You can model your sequential circuit in Verilog. You can describe it in Verilog, and you can simulate it, and you can verify its correctness. Now, what you need to do is that at every state that you have in the state diagram, you have to apply inputs. And you have to apply all the possible input combinations at each state to ensure that the transitions between the states in the state diagram are done properly. You can apply a reset input to reset the circuit to its initial state, and then you can apply a sequence of inputs to test all the transitions that you have in the state diagram. So this is very important when you would like to test a sequential circuit, is that you test the transitions. So you would like to ensure that all the transitions that you have in the state diagram are correct. And then you can observe the output. You can check that the output is correct. You can look at the next state, that the transition between the state and the next state is done properly. You can look at all of these things in the timing diagram, and then you can verify the correctness of your design. Right, so let us take a look at this Mealy state diagram that we have seen for the sequence detector. Now, what we need to do is that we need to choose an input test sequence. So it's up to us, okay, when we would like to test a sequential circuit, is to choose the proper test sequence, and we choose it in a way to test all the transitions that exist between these states. So initially we apply a reset, and the reset will ensure that the initial state is as 0. Now after a reset, you can apply a certain input test sequence. Yani, for example, X can be initially 0. So if you apply 0 here, you would like to ensure that you are making a transition from S0 back to itself. So this way you can ensure that this transition is done properly from S0 back to S0. Now after that, you can apply input, let us say 1. This is 1 here. You would like to ensure that this transition from S0 to S1 is done properly. So you can check, you can verify that you are making a transition from S0 to S1, and this transition will happen at the edge of the clock. Remember that all the flip-flops are synchronized with the same clock, and therefore they change their state at the edge of the clock. Now, once you are in state S1 and you apply 0, then this 0 will take you back to state S0. So you have a transition from S1 to S0. So you would like to check that this transition is working properly. Then you can apply here a sequence of 2 1s. This will take you from S0 to S1 and then from S1 to S2. So you can reach here after 2 1s. So you have a 1 followed by a 1. And this way you can check that you are actually reaching state S2. And then is 0 here. Okay, this will take you from S2 back to S0, and you can verify this transition. So far we have verified all of these transitions except this one. So to verify this transition here, you can apply a sequence of 1s here. Okay, so you go from S0 to S1, then from S1 to S2, and then from S2 back to itself. So a sequence of 3 1s will be sufficient to actually check that this transition is working properly. So you have a transition from S2 back to itself. So this way you can exercise all the transitions that you have in the state diagram. So you can choose, okay, your own input test sequence that will make all of these transitions. And this way you can verify the correctness, okay, of your design, that you have actually a correct circuit that can make these transitions between the states. And at the same time, you can verify that the output is correct. You can verify that if you are in state S2 and the input is 1, then you get the correct output is 1. Otherwise, you would get the output equal to 0 if you are in other states. Or if you are in state S2 and the input X equal to 0, you should really get the output equal to 0. So therefore, you need to also verify that the output of the sequential circuit is also correct. Not only the transitions, but also the output. Okay. So now what you need to do is that you need to apply this input test sequence, and you can look at the what you need to look is that you have to look at this timing diagram, at the waveforms. Okay, so here you have a clock. Okay, and we can choose, for example, the rising edge of the clock, depending, of course, on the types of flip-flops. So if these flip-flops use the rising edge of the clock, so your focus will be on this rising edge of the clock. Before we use the negative edge, because the flip-flops use negative edge. Here I'm using rising edge. So initially, the state here, which is defined by Q1 and the Q0, so we have two flip-flops. So initially, it is unknown. So when you power on the circuit, you don't know what's the initial state. And because the state is unknown, you don't know what's the output. Okay? So you can apply a reset. So the reset is shown here. And this reset is going to ensure that you make a transition to state S0. So when you apply this reset, notice that here that we are making a transition to state S0, or we are starting in a state S0. S0 here, it means that 0, 0. Okay? So it's represented by 2 bits. Already we have done the state assignment before, and we said that S0 is represented by 2 bits, 0, 0. That's actually S0. Okay? Now, if you are in S0 and you apply the input X equal to 0, then the next state will also be S0. So this is also 0, 0. So we are making a transition from S0 back to itself if the input X equal to 0. Now, how do I know the input X? Notice that X is changing over time. What is important to us is the value of X just before the rising edge of the clock. So look at the value of X here. Okay, just here before the rising edge of the clock. So notice that here X equal to 0 before the rising edge of the clock. Here X is equal to 1. Notice that X is equal to 1 here. Here, notice that X is equal to 0. This is X equal to 1. This is X equal to 1. So look at the value of X just before the rising edge of the clock. So here it is 1, 1, 1, etc. 1. So you can look at the value of X just before the rising edge of the clock, and this will tell you what's the value of X, whether X is 0 or X is equal to 1. Now, if you are in state as 0, and the input X is equal to 1, notice that X equal to 1, then therefore you are making a transition from S0 to S1. So we are making this transition. So you can verify this in the timing diagram. So notice that here the next state is S1. S1 is represented in binary by 0 and 1. So notice that we are changing the state at the rising edge of the clock. So this is when we are changing here Q1 and Q0. Now Q1 will remain 0, but the Q0 is jumping from 0 to 1. So this is really happening just after the rising edge of the clock because there's a small delay inside these flip-flops. So their output does not really change immediately at the rising edge. It will change just after the rising edge. So there is a small delay between the clock, the edge of the clock, and the output of the flip-flop, and this delay exists inside the flip-flop. Like we have delays in combinational circuits, we also have delays inside flip-flops. Okay. So it is synchronized with the clock, but it will happen just after the rising edge of the clock. Now, if the next input is 0, if you are in S1 and the input is 0, then you will go back to state S0. So next cycle, we are making a transition from S1 to S0. So you can see that this is 0, 0. And the change will happen just after the rising edge of the clock. Then we apply another one. Okay, then this will take me from S0 back to S1 as before. So this is 0, 1. And then we apply here another one. So this will take me from S1 to S2. So this is 1, 0. Okay. So notice that how Q1 jumped from 0 to 1 and the Q0 went from 1 down to 0. So this change is happening just after the edge of the clock. Now here's the problem. You are in state S2. Notice that the input X is changing from 1 down to 0 during clock cycle number 6. So notice that it was 1 here, and then it went down to 0 during the same clock cycle. Now that's the input. The input here, X, is not really synchronized with the clock. That's my external input to my sequential circuit. So initially it was 1 here, and then it went down to 0. So let me just write down here 1. Okay, so that's actually is 1. And then it went down to 0. So when X was 1, you are in state S2, then the output is 1. So notice that how the output here jumped, the output Z, it went to 1. Okay, you can see that it went from 0 to 1. And then when X dropped from 1 down to 0, you are still in the same state as 2, how the output changed to 0. So the Z output went from 0 to 1, and then it went back to 0. So we got this false output, which we call a glitch. So this is the glitch here. Okay, that's actually is for a small duration of time, we got a wrong output, which is 1. That's a false output. The true output is 0, which is shown here. But we got actually this glitch, which is for a short period of time. Okay, because this can happen in the case of a Mealy sequential circuit. It cannot really happen in the case of Moore, because in the case of Moore, the output is synchronized with the clock. It depends only on the state, and the state is synchronized with the clock. It can happen in the case of a Mealy, because the output depends not only on the state, but also it depends on the input. And the input can change. So you can see how the input X is changing during this clock cycle number 6. So during this clock cycle, you can see that, look at the waveform. So X was 1 and then dropped down to 0. And this actually produced this glitch. Okay. Now notice that here in state S2, okay, so we are in state S2, how the outputs and the input X is equal to 1. It's not really changing. How we got the correct output, which is 1. Without any glitches. So sometimes you don't really get the glitches because the input X is stable, is equal to 1, it's not changing. But sometimes you get the glitches in the case of a Mealy sequence detector or any Mealy sequential circuit. So we have verified the correctness, okay, of the sequential circuit, and we have observed that sometimes we get the glitches, okay, at the output. Do you have any question about this? So this step is important. This is called verification. Okay, so this is if you are simulating this in Verilog, you apply an input test sequence, you can observe the timing diagrams, and you can see, you can verify the correctness of the sequential circuit. And you can look at the transitions between the states, and you can observe all of this from the timing diagram. Right. I have another example about a sequential comparator. Now, a sequential comparator is a sequential circuit. It's different from a combinational. What we have seen before when I talked about combinational circuits, we have seen the magnitude comparator. That was a combinational circuit. Now, I'm going to design a different comparator, which is sequential. And it has two inputs, A and B. But notice that A here and B are just single bit. So basically, we have a bit stream here. We have a bit stream. So my input A, for example, so this might be A. It might be, let us say, 101101. And B, for example, might be, let us say, 010101. Okay, it might be something like this. Okay, so what we are going to do is that we are going to compare A with B bit by bit and produce here two outputs. One is called greater than this indicates that A is greater than B, and less than, this indicates that A is less than B. So these are the two outputs of the sequential comparator. Now here A is a bit stream, so we are going to start at bit 0. So we start here at bit 0 of A and bit 0 of B. So we're going to compare this bit with this bit. So we start at the rightmost bit and we move to the left. So this is how I would like to compare, okay, these two numbers. So cycle by cycle, we provide 1 bit of A and 1 bit of B. So this is done over many clock cycles, and this is why it's called sequential, because we are doing it over time. So A here is a bit sequence and B is also a bit sequence, okay? So we start by comparing A0 with B0, then we compare A1 with B1, etc. So here bit 0 is the least significant bit, and we move all the way from the least significant bit to the most significant bit. Now, before we start our comparison, we need to reset. This reset is very important to start in the initial state, in the start state before the comparison starts. So we always need a reset. So this reset is connected to the flip-flops that exist inside the sequential comparator. We also need a clock because we need to synchronize the sequential circuit with the clock. So this clock is also connected to the flip-flops. So the clock is very important because cycle by cycle, we are going to change. Okay, so initially, we have A equal to 1, B equal to 1. Next cycle, A becomes 0, B equals 0. So we move here to this bit 1, then bit 2, then bit 3, etc. And then after repeating this for n cycles, then we are comparing n bits of A with n bits of B. So we are doing it cycle by cycle. We compare 1 bit of A with 1 bit of B. Okay, so we are going to have two outputs. The first output is called greater than, and the second output is called the less than output. Okay, so every time I would like to start a new comparison, I need to reset my sequential comparator, and then we can start a new comparison. So once we finish one comparison, we can start the next one after a reset. Okay, this is the importance of reset. So now the question is, how do we design this sequential comparator? So this is the problem description. And now what we need to do is that we need to go through the steps of design. So what was the first step of design? What should we do first? The first step in the design procedure. What's the first step in the design procedure? Is to obtain what? The circuit? Or what? Students, what's the first step in the design procedure?
To obtain the equations.
Before the equations. The first step,
graph?
step number 1.
What is it called? I forgot the name.
Okay, I cannot hear you, Ahmed. Can you say that loudly?
Graph, or I forgot its name, but
what's the name of that?
I forgot it.
Students?
The formulation, I think.
Well, this is not a combination circuit, this is a sequential circuit. The first step in the design of a sequential circuit is what? Is to obtain, so this graph is called what, Ahmed? The
state diagram?
Yes, thank you.
Yes.
The state diagram. So the first step is to design the state diagram. If you do it correctly, then the remaining steps will be easy. But the first step is the state diagram, and we have to do it properly. So we need an initial state. Notice that here I only have two outputs, greater than and less than. Now we have three possible outputs. Either you can have greater than. So you have here greater than equal to 1 and less than equal to 0. Or you can have less than, and it means that GT will be equal to 0 and LT will be equal to 1. That indicates that A is less than B. Or we can have 0, 0. That indicates equality. And it means that it's not greater than, it's not less than. So this indicates equality. So we have three possible outputs. 0, 0 indicates equality. 1, 0 means greater than. 0, 1 means less than. Okay. So these are the three possible outputs that you can have for this sequential comparator. One thing for sure is that you cannot really have a greater than and less than to be both 1 and 1 at the same time. So this output is not really possible. You cannot really have A is greater than B and A is less than B at the same time. So you cannot really have both the GT and the LT outputs to be 1 and 1 at the same time. So now what I would like to reset, before I start my comparison, okay, what we need to do is that we need to say we have to make an assumption, okay, before we have compared any bits of A and B. So let me start here. This is actually A, okay, and this is B. So let me put some bits here for A and B. Let us say this is 1, 0, 1. This is 1, 0. I don't know, 0, 1. I'm just going to put some numbers here. And this is 0, and this is 0, and this is 1, and this is 0, 0. Let me just put 1 here and 0, 1. Okay. So I would like to compare these numbers here. I might also have additional bits if I would like to. So we're going to start, before we start our comparison, we're going to assume equality. So when we reset, okay, we start at the initial state, and the initial state indicates equality, okay, that A is equal to B. So before I make any comparison of any bit, I need to start somewhere. And this somewhere here, this is my initial state, indicates equality of A and B. Now, equality means that the output should be 0, 0. That's the meaning of equality. So here I'm showing the output inside the state. So this is a Moore design, okay, showing the output inside the state. So now I'm going to start at the least significant bit. I'm going to start at bit 0. I'm going to start by comparing here A0 with B0. So they are actually 1, 1. I'm going to remain in the same state. So if A is equal to B, and A equal to 0, B equal to 0. So we have AB equal to 0, 0. So this is AB. Or AB equal to 1, 1. This indicates equality. So we have a transition from the state back to itself. That indicates equality. Now, if we have A equal to 0 and B is equal to 1, so here, for example, when we move from this bit to this bit here, so this is also 0, 0. That indicates equality. So first we reset, then we have 1, 1. So we have a transition from equality back to itself. That indicates equality. Then we receive 0, 0. They are still equal. But then next cycle, I'm going to receive 0, 1. So 0, 1, this indicates that A is less than B. So I have to make a transition from equal to LT, indicating that A is less than B. So here, notice that the output is 0, 1. 0 here means that it's not greater than, and 1 means it is less than. Okay, so 0, 1, we have two outputs, greater than and less than. So the less than output will be equal to 1. Okay, that's the meaning of 0, 1. Next, if I get, let us say, 1, 0, on the other hand, this will take me to greater than. This indicates that A is greater than B. So this is the greater than output, and this is the less than output. So we got 1, 0. That indicates greater than. Now notice that if you are in less than or a greater than, and you get the input is reversed, and for example, if you are here in less than state, and the input is, let us say, is 1, 0, like here, for example, the input is 1, 0. So when we move to the most significant bit and we get 1, 0, this will take me to greater than. This indicates that now A is no longer less than B. It's now A is greater than B when we are moving to the most significant bit. And vice versa. Okay, if we had it the other way around, we will move. If we get actually 0, 1, then this will take me from greater than back to less than. If I am in the same state here, for example, if I am in greater than, and the next input is 0, 0 or 1, 1. Okay, so here I have 1, 1. Here I have 0, 0. Then this means that I'm going to remain in the same state. So notice that 0, 0 or 1, 1 or even 1, 0. Notice that here we have 1, 0. It is still greater than. Nothing has changed. Okay, so even though the upper bits are identical, we still have A is greater than B and we remain in the same state. However, if we get 0, 1, then we have to change state. And if we get, for example, here is 0, 1, then A is no longer greater than B, so A becomes smaller than B. So we have to make a transition from greater than back to less than. And similarly, if we are in less than and the inputs is 0, 0 or 1, 1 or even 0, 1, then we remain in the same state, indicating that A is less than B. So this is how we complete the state diagram. At any state, we have to show all the possible inputs and all the possible transitions, okay, to make this state diagram complete. Otherwise, the state diagram will be incomplete. Okay. So this is the first step, is to design the state diagram. Next, we have the state diagram. What shall we do? What is the second step?
The state table.
Yes. So we need the state table, and at the same time, we have to do state assignment. So let us do this. So notice that. Let me clean up this slide here. So notice that this is a Moore state diagram. And notice that the output is shown inside the state. So we have two outputs. We have the greater than output and we have the less than output. And these are shown inside the state. Now what we need to do is that we need the state assignment and the state table. Now the question is, how many flip-flops do I need? Okay. I should have asked this question in the previous slide. Well, clearly here we have only 3 states. So 3 states, it means that we need 2 flip-flops. And the reason why we need 2 flip-flops, because 1 flip-flop is not enough. If you use 1 flip-flop, you can only have 2 possible states, 0 and 1. But here we have 3 states, and therefore we need 2 flip-flops. So we're going to use D-type flip-flops because these are the simplest to use in a sequential circuit. And we need to do the state assignment. So what will be the state assignment for equal, for less than, and for greater than? Now, the simplest state assignment, because this is actually more, is to make the assignment identical to the output. Yani we can actually make this equal here. We can make it 0, 0. And I can make this less than here to be 0, 1. And greater than becomes 1, 0. So if you do this state assignment, you can make the output identical to the present state. And this can simplify the output logic. And this is great. Okay, so we are going to choose the state assignment to be identical to the output. Okay, and the reason why we are doing it like this is to simplify the output logic. So we can take the output of the flip-flops, and this is the present state, and this is also the output of the circuit. Okay, so that's basically is the state assignment. So now what we need to do is that we need to fill the state table. So we have 3 states, 0, 0, 0, 1, and 1, 0. Now notice that state 1, 1 is unused. We are using 2 flip-flops. Because we are using 2 flip-flops, you can actually have 1, 1 as a possible combination of Q1 and the Q0. So here Q1 and the Q0, these are the outputs of the 2 flip-flops, and this is my present state. Whereas the next state here is D1 and D0, these are the inputs, okay, to the D flip-flops. So now we have state 1, 1 is unused, okay? Because we have 2 flip-flops, we have 4 possible combinations. So 2 to the power 2 is equal to 4, but we are only using 3 states, so the last one is unused. Sometimes you might actually get more unused states, depending, of course, on how many flip-flops you are using and how many states you have in the state diagram. Right. So what we need to do is that we need to fill this state table. So we look at all the possible inputs. So we have 2 inputs, A and B. So I'm showing here 4 columns, 0, 0, 0, 1, 1, 0, and 1, 1. And what we need to do is that we need to show the transitions between these states. So if you are in state 0, 0, that indicates equality, and the input is 0, 0, or 1, 1, then we make a transition back to state 0, 0. So notice that here we have a transition to state 0, 0. On the other hand, if the input is 0, 1, we make a transition from 0, 0 to state 0, 1. If the input is 1, 0, then we make a transition to state 1, 0. So we fill the state table according to the information which is given in the state diagram. Okay, so we are just copying the information from the state diagram into the state table. Now notice that in the case of the last state, which is 1, 1, this is unused state. I'm showing here don't cares, okay, because this state should never be reached. It does not exist in the state diagram, but it is a possible combination. Yani Q1 and the Q0 can be 1, 1, but we should never reach the state 1, 1. So for this reason, I'm showing that the next state is a don't care, because we are not really supposed to be in state 1, 1. So regardless of my input, I don't really care about my next state. So I'm showing it as don't cares. So this is here my state assignment and state table. Now, once we have, notice that I'm not really showing the output because the output is identical to the state. Okay, so the output here is equal to the present state. The output is equal to Q1 and Q0. So for this reason, we don't really need to show the output because it is trivial in this example. So what is now left? What is the next step? We have the state table. We have done the state assignment. What should we do next?
Use the Carnot map.
Yes, we use the Carnot map to obtain the equations. So what we need to do is that we need to derive the next state equation. So I need the equation for D1, and I need the equation for D0. So we're going to copy, okay, the content of this state table into the Carnot map. So the D1 here will be the first column. This is D1. So it is shown by these 4 columns. So that's here the most significant bit. And of course, D0 will be the other 4 columns. So I need to copy these 4 columns into the Carnot map. But we have to be careful here. So this Carnot map will be 4 by 4. It's actually, it has 16 squares. Because we have Q1 and the Q0, this is my present state, and A, B are my inputs. So, but we have to be careful about how we fill this Carnot map, because in the case of the Carnot map, we place row 1, 1 before row 1, 0, whereas here 1, 1 is appearing at the end. So notice that here for 1, 1, all the D1 is equal to don't cares. The same thing here, D0 is equal to don't cares. So we have 2 Carnot maps, one for D1 and one for D0. The same thing is that here column 1, 1 appears before column 1, 0. So we have to be very careful because this depends on A and B. Here I'm showing A, B equal to 1, 0 before 1, 1, but I'm just interchanging, switching their order, okay, inside the Carnot map. So notice that here we take this column here and we have it here. This is actually for column 1, 1. And this is column 1, 0. And you have to make sure also that we have switched the order of row 1, 1 with row 1, 0. So make sure that you don't really make this mistake. So notice that in the case of 1, 1, this is 0, 0 here, right? That appears 0, 0. Now this one here is copied here. You can see this is the 1. Okay, I don't know if this is clear. And this is the don't care. In the case of 1, 0, when the input is 1, 0, so we have here 1, 1. Here I have a 1, and this is a don't care. So you have to make sure that you fill this Carnot map properly. You don't really want to make any mistake when you are filling the Carnot map. You do the same thing for D0, but the D0 here will be the other 4 columns. Okay. So what is shown here in the state table is that it is showing the next state, which is basically we have D1 and we have D0. So basically the most significant bit here is the D1 and the least significant bit is D0. So we have these two different Carnot maps. And once we have the Carnot maps, then we can obtain the equations. So we can obtain the equation for D1, and we can obtain the equation for D0, and we can obtain minimal sum of product expressions. So here is the expression for D1. Now notice that here I have Q1, Q1. You can even factorize Q1 and you get A or B prime between parentheses. Now this is no longer sum of product. This is more like a three-level expression. And here you can obtain a minimal sum of product expression for D0, but you can take here Q0 as a common factor, and you have A prime or B. So this is, again, is a three-level sum of product. This is not no longer sum of product, it's a three-level expression. So the first one here is a sum of product expression, but the second one is no longer sum of product because we took Q0 as a common factor. So it's no longer and or expression, it's or and or. Okay, so it's a three-level expression. So we have the equations. We obtained them. These are minimal expressions that we have obtained from the Carnot map. You can decide to implement the sum of product, or you can do the factorization and implement this. Now, what's interesting here is, so once we have these expressions here, okay, so once we have these expressions, we can implement the sequential circuit. This is the sequential circuit. This is the sequential comparator circuit diagram. Okay, so we have all of this logic is used here for D1. So notice that this is Q1 here. So we can write Q1 here. This is Q0. So I can write here Q0. So notice that how we are feeding here. So we have these two D flip-flops. Notice that how the clock is connected to both flip-flops. So both of them are going to change their state at the same edge of the clock. Notice the reset input. So when you would like to draw a circuit diagram, do not forget the clock and the reset. So the reset is very important because you would like to reset and start at the initial state. So you can actually have A, here you have A prime. Here you have B, here you have B prime. And so on. Okay, so so you can connect. This is also B prime. Okay, and you can obtain the equation here for D1. That's the equation for D1, which is implemented by this logic. And we have the equation for D0. Now, all of this logic here, all of this, okay, is my next state logic. Okay, so I'm not sure if you can see that clearly, but let me just erase the ink and draw it again. Okay, so this is my next state logic because we are using this logic to produce D1 and D0. And D1 and D0, these are the inputs to the flip-flops, and this will be my next state at after the rising edge of the clock. Okay, so remember that the inputs to the flip-flops define the next state. Okay, and this is what will be the output, okay, in the after the rising edge of the clock. Notice that the outputs Q1 and the Q0 are nothing but greater than and less than. So the outputs of the sequential circuit are identical, okay, to the outputs of the flip-flops. So we have designed, okay, the sequential comparator to be a more designed so that the output logic is simplified. Okay, it's very simple. So now we have this circuit. We can, of course, model the circuit in Verilog, and we can simulate it, and we can verify its correctness. So what we have seen is that we have seen two examples, okay, one about the sequence detector, and also we have seen the sequential comparator in which we had unused states. So we can design a circuit that has unused states. So when you are designing the state diagram, okay, the number of states might not be a power of 2. But when you would like to implement this using flip-flops, okay, if you decide to use n flip-flops, then you will have 2 to the power n is the number of binary states. So if you use n flip-flops, then the number of binary states will be 2 to the power n, because each flip-flop can store a 0 or a 1. So you have 2 to the power n possible combinations. However, in the state diagram, you might have m is the number of states. Like, for example, we have seen 3 states in the case of the sequential comparator. Also, we have seen 3 states in the case of the, remember the sequence detector that used the Mealy sequence detector, we only had 3 states. So if you have, let us say, 3 states, but you are using 2 flip-flops, then we had 1 unused state. So in general, you can say that the number of unused states is 2 to the power n minus m. Okay. In our example, we only had 1 unused state, but sometimes you might have, let us say, 5 states. Okay, 5 states in the state diagram, and you are using 3 flip-flops. You cannot use 2 flip-flops. If you have 5 states, you have to use 3. If you use the 3, you will have 8, 2 to the power 3 is equal to 8. So 8 minus 5 will give you 3. So we'll have 3 unused states. Now, these unused states do not appear in the state diagram, like we have here. If I would like to go back, okay, to, let me discard all of this and go back here, okay, to the state diagram, you can see that there are only 3 states. So there is 1 state here which does not appear, and this is unused. Okay, you can see that also here. Just go back, okay, to the equations. So you can see that here state 1,1 here is unused. So this is unused. And we place don't cares here, okay, because this state is unused. We did not really care about the next state. But we have to be careful about this. So, so we use these don't cares to simplify the equations. So this is what we did, okay? In the case when we had unused states, we can treat them as don't cares, okay, the next state, and we can use the don't cares to simplify the expressions in the Carnot maps. However, okay, a careful circuit designer, okay, will have to worry about these unused states. Okay, we might enter an unused state because we have some kind of interference or a circuit malfunction. So this state here, which is shown here in the state table, which is 1,1, we are not really supposed to reach this state. This state is unused. We can never have, okay, A is less than B and A is greater than B at the same time. So this actually 1,1, state 1,1, indicates that A is greater than and less than B at the same time. But that's not really possible. So, so for this reason, we did not really have this state, and this is why we use don't cares. But sometimes, when you power on, let us say, a sequential circuit, and you connect the power supply to these flip-flops, their initial state might be 1,1 before you reset, or you might actually have some kind of interference. So rather than being in a state 1,0, you might actually have the 0 flipping to a 1 because of some kind of interference, and you might enter an unused state which is 1,1. Okay, so this might be possible to enter an unused state. Sorry. Because we have outside interference, or you have a circuit malfunction. So what you have to do is that you have to specify. So if you are in an unused state, we use here the output to be identical to the state. So the output indicates that the output is 1,1, indicating that there is a clear malfunction of the circuit, because you cannot really have a greater than and less than to be 1 and 1 at the same time. So we can use a special invalid output can be used to indicate that we are in an unused state. And if by accident we enter this unused state, the output will show it. Okay. Now, rather than using here don't cares to return back here to make a transition, we can force these to be 0, 0. By forcing them to be zeros, then we can ensure that if by accident we enter an unused state, we will be able to return back to the start state. So we don't really want to make a transition from an unused state back to itself, because then in this case we'll be stuck in an unused state. So for this reason, okay, it is better when you are designing with unused states is to return to a valid state, or sometimes the reset state, okay, or the start state, even without doing any reset. Okay, so this is actually good. Rather than using don't cares, what you need to do is that you need actually to use zeros, okay, as the next state. If you enter an unused state, that can ensure that you are going to exit this unused state. Okay. Let me give you my last example for today, and I would like to conclude with this example. I would like to design a 2-bit up-down counter. So we have here two inputs, enable and up. If the counter is enabled, then we will count. Otherwise, we will remain in the same state regardless of the U input. So here U means up. If U is equal to 1, we count up. If U equal to 0, we count down. So when we count up, if E and U are equal to both 1 and 1, then we count up from 0 to 3 and then back to 0. Yani 0, 1, 2, 3, 0, 1, 2, 3, like this. On the other hand, if EU equal to 1, 0, then we are going to count down. Yani we start here at 3, then we go back to 0, 1, so 0. So basically we go down from 3 down to 0, yani 3, 2, 1, 0, then 3, 2, 1, 0, like this, backwards. So this is a countdown. I'm going to talk about counters in a great detail in a later presentation, but I'm going to show you how we can design such a counter, okay, using just by drawing a state diagram. You can design this counter using D-type flip-flops or T-type flip-flops. Okay, you can choose the type of flip-flop. T-type flip-flops actually are really good for counters, and we can use also a reset, okay, to start in the initial state. So let us design the state diagram. I want to conclude actually with the state diagram. So we need 4 states. So these are 4 states because this is a 2-bit counter. So we count from 0 to 3. So these are states S0, S1, S2, S3. If it is enabled and it is counting up, we go from S0 to S1 to S2 to S3 and then back to S0. So notice the direction of the arcs. So this is when it is enabled and we are counting up. On the other hand, if it is enabled and we are counting down, okay, if we start at S0, then we have to go backwards to S3, then to S2, then to S1, then back to down to S0. So we are counting backwards. So this will be a down counter. Okay, so we can count up, we can count down. And if it is not enabled, if equal to 0, we remain in the same state. We don't change the count value. Okay, then this is actually when E equal to 0. And then we have a reset, okay, that will start initially at state S0. We can take the state diagram, and as we have done before, we can actually assign binary codes. We can do the state assignment. So for example, state S0 can be 0, 0. This will be 0, 1. This will be 1, 0, and 1, 1, and then you can fill the state diagram. Once you have the state diagram, you can actually obtain the equations using the Carnot map. So you need actually the equation here for D. So the next state here will be D1 and D0. So you need actually 2 Carnot maps, one for D1 and one for D0. This is if you would like to implement it using D-type flip-flop.